So this is a problem involving our SUVAT equations. So it says a ball is projected horizontally at 5 meters per second from a vertical cliff of height 110 meters. Assume that air resistance is negligible and use gravity to be 10 meters per second squared. The first question is to state the magnitude of the horizontal component of acceleration of the ball after it leaves the cliff. So once the ball leaves the cliff, the only force of acceleration that is acting upon it is gravity. There's no horizontal acceleration, so therefore the magnitude of the horizontal component of acceleration is 0 meters per second squared. Next one, on the axis below, sketch graphs to show the horizontal and vertical components of the velocity Vx, Vy, and Vy change with time until just before the ball hits the ground. It is not necessary to calculate any values. So the horizontal component of velocity, again, because there is no acceleration in the x direction, doesn't change. So it's initially stated at 5 meters per second because we don't have to do any calculations. Again, because there's no acceleration, the velocity is going to remain at 5 meters per second. So we can simply just draw a horizontal line to represent that as time progresses, the velocity in the x will remain at 5 meters per second. The vertical component, however, is being acted upon by an accelerating force. So right before the ball leaves the table, the vertical component is going to be 0. So it's going to start at the origin. However, as time goes on, again, acceleration is the rate of change of velocity, so velocity is going to increase every second, in this case by 10 meters per second. So if we start this at the origin and just make a straight line that goes upward, it indicates that as time goes on, the velocity is going to increase after every second. B says to calculate the time taken for the ball to reach the ground. So for this we can use our trusty SUVAT equations. So if we set up SUVAT, we have to make the y and the x separate. So we don't know the final x distance that the ball will travel, so we don't know this. The initial velocity in the x, they state as 5 meters per second. Again, there is no acceleration, which indicates that the velocity will therefore remain the same. So the velocity, the final velocity is again 5 meters per second, and we don't know the time. And the y, the s is the height, which they give to us as 110 meters. The initial velocity in the y is again 0 meters per second. However, because there's an acceleration, which they give to us to be gravity, which is 10 meters per second squared, this velocity is obviously going to increase, though to what we don't know, and we don't know the time. So we are going to use the y component of SUVAT to solve for time because we have 3 different values. So we can use the equation s equals ut plus 1/2 at squared to solve for time. The initial velocity is 0, so this entire ut goes out to 0. So we therefore just have s equals 1/2 at squared. We plug in values, we have 110 meters as our distance equals 1/2 10 t squared. So t is going to be the square root of 110 over 5, which gives you t equals 4.69 seconds. And that is your answer for B. For 2, it says to calculate the horizontal distance traveled by the ball just before it reaches the ground. So that, referencing our above SUVAT setup, is the distance in the x. So if we have time, if we have these values right here, and we now have time, we're able to solve for s using the same equation as above. So again, s equals ut plus 1/2 at squared. Again, because there is no acceleration, this 1/2 at squared goes to 0. So we now just have s equals ut. Plugging in values, we have s equals u, which they gave to us as 5 meters per second, times time, which we just calculated to be 4.69 seconds. So our distance in the x is approximately 23.5 meters. The final problem asks, it says another projectile is launched at an angle to the ground in the absence of air resistance. It follows the path shown below, and it says on the diagram above, sketch the path that the projectile would follow if air resistance were not negligible. So if it were not negligible, air resistance, there's a force between the object that's following and actually the air molecules that are pushing up against it. So the acceleration in the y direction is going to be less. So not only will our final height be lower than it would be otherwise, but it's not going to travel an x distance that's as great as it were before. So what this looks like in a graph is it's just going to be lower and lower, and that is it. So thank you.